Good morning. Hopefully, you guys got through the pre-stoichiometry review okay. It was all things that we did last semester, so hopefully it was a refresher for you and it kind of brought it all back to the front of your minds. So today we're going to get started on stoichiometry. And I know we've kind of been talking about this all year, about how this is going to be a difficult unit, and I'm not going to lie to you and say that it's easy. This unit can be difficult because it just has so many little working pieces. And you have to have those basic skills of balancing equations, writing formulas, and dimensional analysis down before you can really understand stoichiometry. But in a bigger picture, once you have all those basics down, stoichiometry is just another way to convert the amount of reactants into the amount of products. So it's very useful in chemistry and in some other examples that I'm going to show you here. So today we're going to talk about stoichiometry. We'll talk about mole ratios and why that's important, and then how to actually do these problems. So stoichiometry is pronounced stoichiometry, okay? So what is it? It comes from the Greek word stoichion and metria, which is just a measure of an element, okay? And that's important because that's all stoichiometry is. We're just finding out how much of something can be produced. So what is it used for? Mostly it's just used for calculating quantities of materials used and produced in chemical reactions. That's obviously really important. So if you are a scientist or an engineer or a farmer or anything else that you might need to purchase a product and use it and figure out how efficient that's going to be, you're going to want to be able to use stoichiometry in some form or fashion. Okay, so it might help you figure out like what type of material to use to make it cost efficient, or how much you might have to spend to get a certain amount of product. So what example here is this career in chemistry is farming. And I know that most of the time you probably don't think of chemistry when you think of farming, but agriculture has a lot of chemistry. So if you're already in ag programs or you already have farming families, you probably know that already. But if you're not super involved in that like lifestyle, then you probably don't know that. So in farming, lots and lots and lots of chemistry, especially with the soil. So the farmers, it's actually an entire job to be like a soil expert. I don't know the name for it, but there's people that are hired to go out and test soil samples and then determine what these farmers would be best to purchase and put in their fields to get a better yield. So in this example, we have corn, and we are very familiar with corn around here. So corn is one of the products that actually removes a lot of phosphorus from the soil. Okay, so for this reason, farmers usually will rotate their crops. So they're either going to do like corn one year and beans the next year, or they're going to have to add a bunch of fertilizer to the ground before planting corn again the next year. So corn's removing this phosphorus from the soil. You have to replenish it somehow, either by rotating crops or adding fertilizer. So on average, 1 acre of corn will remove 6 kilograms of phosphorus from the ground. And so we're going to use that later on. So let's assume that you're going to inherit a farm, and you have to now figure out how much fertilizer to purchase for the farm and how much that's going to cost you. This farm is 340 acres and had corn planted last year. So you have to add fertilizer to the soil before you plant this year's crops. You go to your local fertilizer supplier and find superphosphate brand fertilizer. Reading the bag, you see this molecular formula. Okay, so you're familiar with molecular formulas. We've been looking at these things all year. So you have to decide how much fertilizer to buy for the application to your cornfields. Okay, so you know that 6 kilograms of phosphorus are being lost per acre. You know that your farm is 340 acres, and you know the molecular formula here. We obviously know how much these bags of fertilizer are going to cost us. So $54.73. We need to figure out how many bags of fertilizer you need to purchase, and then how much is going to cost to purchase that many bags. So some things that we are given or information that you could find for your conversions here is that 1 bag of fertilizer weighs 10,000 grams, and then we know that 454 grams is equal to 1 pound. So in this next slide, we're going to kind of work through this problem. So how much fertilizer will you need? That's where we have to start, right? So for our conversion factor, we know that 1 acre of corn is going to remove 6 kilograms of phosphorus. Okay, so that's right here at the top here. So if you have 1 acre of corn, you're going to need 6 kilograms of phosphorus for every acre. So we're just going to figure out how much phosphorus we need total, grams of phosphorus specifically, because if you remember in this problem, it just tells us that 1 bag of fertilizer is 10,000 grams. Okay, so everything's being measured in grams in this scenario, so we're going to convert it into grams. So we know we're going to start with 340 acres. That would be in the top part of your table, and you probably noticed that this is set up kind of in a slightly different format than the format we've been using. I would normally draw this out as a table, but this is a resource that I have on here, and I need to probably retype this so it's exactly the same way, but either way. So this 340 acres is going to be in the top box of that table. Acres is the unit that we're starting with. Okay, so acres has to come down and across. That always happens with the dimensional analysis. Now we need to figure out what our next step is. Well, this conversion factor tells us that 1 acre is equal to 6 kilograms of phosphorus. So we can write in this 1 now. You're almost always going to be putting down the unit before you put in the number for stoichiometry, because we're going to have to be looking at ratios of things before we can determine what numbers will go there. So we wrote acres here. Acres comes down. We use this ratio of 1 to 6. So now I know that 1 acre is equal to 6 kilograms of phosphorus. Now acres would cancel. Now I am in kilograms of phosphorus. We need it to be in grams for the latter part of this problem. So we're going to go ahead and convert this into grams. So kilograms of phosphorus unit has to come down over here. Now we're going to start looking at that ratio or the conversion factor here. So if we're going from kilograms to grams, we know that there are 1,000 grams in 1 kilogram. So we're going to put that in there. Kilograms of phosphorus will cancel. Now we're in grams of phosphorus, which is what we wanted, and we can solve this. So you would multiply everything across the top, multiply everything across the bottom, and divide these. So we know now that we need 2.04 times 10 to the 6 grams of phosphorus to cover our entire field. So if a bag of fertilizer has this formula, the molar mass is going to be 596 grams, and you guys know how to figure out the molar mass. Okay, so we're just adding all of this up. So if you have 3 calciums, and they're each 40 grams, you have 2 phosphorus, each of those are 31 grams. I'm getting this from the periodic table. Okay, these are rounded quite a bit here, but that's okay for this type of problem. So here you have all the individual masses of all of the elements within this formula, and then you would add them together to get a total of 596 grams. Okay, so moving forward to the next part of it, we need to figure out what percent of this formula is actually phosphorus, because all of the rest of this is great and it's going to be good for the field, but what we specifically need is the phosphorus. How much of that can we get from here? So in this is going to be your percent composition. We did this last semester. So if you have 62 grams of phosphorus in this formula divided by the total mass of the formula times 100 is going to give you 10.4% phosphorus. Okay, so at this point, we know we need this many grams of phosphorus to cover our field, and we know that each bag is 10.4% phosphorus. So for the next step of this, we're still trying to figure out how many bags do we need and how much is it going to cost. So in a bag of fertilizer, you're going to have 10.4% phosphorus, and a bag of fertilizer is 10,000 grams. Okay, so we already knew that, this part from the last page. So we need to figure out how many grams of phosphorus are in every bag of fertilizer. Okay, so we're working our way back, kind of circling back around to the mass needed, so then we can multiply that by the cost. So if we have 10.4% of 10.4% of phosphorus for every 10,000 grams, that's going to give us 1,040 grams of phosphorus per bag of fertilizer. Okay, so now this is useful, right? So we know how many grams of phosphorus are in each bag. We know from up here how many grams of phosphorus we need total. So you're going to take the need divided by the half. Okay, so you need 2.04 times 10 to the 6 grams of phosphorus, and you have 1,040 grams of phosphorus per bag. So that's going to tell you that you need 1,962 bags of fertilizer to completely rebuild up the phosphorus in your field. Okay, so now that we have the amount of bags of fertilizer that we need to be sufficient to get that phosphorus back up, you can then multiply that. So in the very bottom here, you have 1,962 bags of fertilizer times $54.73 per bag to give you a total of $107,000. Okay, so it's going to cost you roughly $107,000 to fertilize this field. So now this farmer can at this point decide whether or not that is cost effective, whether they want to maybe try something else that might have a higher phosphorus content or is less costly. But this is stoichiometry. So obviously what you see here are several moving pieces, right? So these are like the ultimate word problems, if you will. So some people really, really love this because it is kind of meticulous and you go step by step through these. Some people really hate it because there's so much to keep track of. But the way that we'll do it in chemistry will be a little more linear than this. You'll be able to kind of see the whole picture at one time. So we'll go through some examples of that. But this is just one application of like a real life example of what stoichiometry is used for. So I promise I am not just adding this in for no reason. Stoichiometry is very, very important in chemistry, and it's very, very important in any field that would be using any kind of chemistry. So for reaction stoichiometry, based on the law of conservation of matter, we have to start with a balanced equation, okay? So when we're talking about reaction stoichiometry, I'm referring to a chemical reaction, okay? So the formulas, the reactions we've been writing out, and then balancing, that's what we're looking at. So when you have a balanced equation, that's going to tell you how many moles there are of each reactant in each product. Okay, so if you look at this very basic example down here of brownies and eggs, we start with 2 boxes of mix plus 12 eggs will yield 2 batches plus 8 leftover eggs. So we know the ratio. We know that for every 2 boxes of mix, I'm going to get 2 batches of brownies. Or for every 2 boxes of mix, I'm going to have 8 eggs left over. So these are going to be very useful ratios for your conversions in stoichiometry. So the mole ratios is what I was just referring to. This is going to be your relation of the amount of any 2 substances in your reaction. So you will find this in your balanced equation. So balancing equations, being able to write out your equations correctly and then balance them correctly is like an absolute essential skill to be able to do before we can be successful in stoichiometry. So I know we have done this a lot and we spent all of last class reviewing it, but if you are still not understanding this, it is 100% absolutely necessary for you to get help. So either you can talk to me, we can set up a Zoom, you could stop by after school one day, we could schedule a day, you could find a friend in class that you know that could help you with it. But this is very, very necessary. There's also a lot of videos on YouTube from like Khan Academy, or like there's others that are really good. So if you're really struggling with those essential skills, it is definitely necessary to get that kind of hammered out before we can be successful in this unit. So anyway, so what we know from this balanced equation, so the green here, we have 2 moles of aluminum oxide decomposes into 4 moles of aluminum and 3 moles of oxygen gas. Okay, so that's, you would have been given the formula, you would have balanced it, and you would have been done with that part. So possible ratios you could use. Okay, we know that 2 moles of aluminum oxide are going to be equal to 4 moles of aluminum. Okay, so 2 moles over here is going to yield 4 moles of that. You could also say that 2 moles of aluminum oxide is going to be equal to, or it will yield 3 moles of oxygen. And then you also can use this ratio that 4 moles of aluminum would be necessary or left over with 3 moles of oxygen. So 9 times out of 10, you're going to be comparing what your reactants are compared to a product that's going to be given. So an example of this, and this is the best way to learn these, is just by doing them. And I know that this seems cumbersome and it seems like I may be overwhelming at first, but the only way to get good at this is to practice it. And if that means that you're struggling through it and you're failing at it, and then you figure it out, then that's just what it is. There are very few people that get this on the first try. Okay, so if you are working at this and you just can't figure it out and you keep getting stuck, I promise you'll get it if you just keep trying. So don't forget that the keys, the answer keys for all of the assignments are always on the following day agenda. It's like the first thing, and I make it a hyperlink. So if you're working on this assignment today, whenever tomorrow's or the next class day is posted on Canvas, you can just get on there and click on the agenda and then see what the answers are and kind of compare them to yourself. And I want you to do that, okay? I want you to always be checking those answer keys and checking your work to make sure that you are where you need to be, so that we're not at the end of the unit and you have no idea what's going on. So anyway, this first example, what mass of carbon dioxide is needed to react with 3 moles of water to produce fructose and oxygen? Okay, so here you have all of these formulas already written out. You just need to write it out as an equation and then balance it. Okay, so as a reaction, I guess I should say. So you have your carbon dioxide plus your water yields fructose plus oxygen. You would have gone back in and balanced this, okay? Now we have mole ratios. So specifically, we only need the mole ratio between the things that we're looking at, like what's being asked in the question. So what mass of carbon dioxide is needed to react with 3 moles of water? Okay, so that is really important. So we are just looking at the carbon dioxide compared to the water. So that's the only mole ratio that you really need from this one. So when we look at these, we have 6 moles of carbon dioxide is going to yield, 6 moles of carbon dioxide is needed, and you have to react that with 6 moles of water to be able to produce your products. So that's your ratio that you need here. So 6 to 6. Now the next part is the stoichiometry, okay? So for this one, you put in what you start with in your dimensional analysis. So it's given here in this question 3 moles of water, okay? And these problems are a little tricky. You need to read through them carefully to be able to identify like what it's asking for. So 3 moles of water is what is given here. It's what we're going to start with. So I have 3 moles of water. You have to have both of these on here. And I know some of you guys are just really resistant to not wanting to write in all the units, but you absolutely have to with stoichiometry. It is required. So for here, you have to have the moles, which is the unit, and some designation of what you're talking about. So the formula, the chemical formula, or the element here. So here we have 3 moles of water. Moles of water is the unit that has to come down and over. So in stoichiometry, you're going to write the unit first and then write in the number. Okay, so don't even write a number in here until we write in the units. So moles of water comes down. Now we have to figure out, like, if we're trying to find the mass of carbon dioxide that's needed, and we have this, we already have our mole ratio right here. All right, so it's a 6 to 6 ratio. Leave it at 6 to 6. Okay, don't change it to 1 to 1. Don't reduce this because in the end, it could mess things up later on whenever we have more complicated problems. So don't reduce the ratio. So we know that there's 6 to 6 here. So 6 moles of carbon dioxide is equal to 6 moles of water. So at this point, moles of water would cancel, okay? So now we're in moles of carbon dioxide, but the question's asking for mass, okay? So what mass of carbon dioxide is needed? So now we just need to convert these moles of carbon dioxide into mass of carbon dioxide. So here we have moles of carbon dioxide, that unit comes down, okay? So moles of carbon dioxide. Now we need to figure out the mass of carbon dioxide and put that on the top. So again, we're just adding these up from your periodic table. You'd have the mass of carbon plus the mass of 2 oxygens to get a total of 43.99 grams. So at this point, the moles of carbon dioxide would have canceled. We're left with grams of carbon dioxide, which is what we need. So we're done with the dimensional analysis. You just have to solve it. So you'd have 3 times 6 times 43.99 divided by the 6 times 1. So that should give you 131.97 grams of carbon dioxide. This is important, okay? So when we're doing labs, or if you're ever in a lab in college, or you're working in a field where you're going to be completing chemical reactions, you need to know how many reactants you need to begin with in order to yield the products, right? So if you're going to start with 3 moles of water, how much carbon dioxide do we need to start with to be able to get our results that we need? Okay, so that's kind of the idea here. So we are just starting out with just mass to mass problems today as far as the assignment goes. So we'll talk about a couple of different ways to approach these problems. Just like any other set of dimensional analysis problems, there's not just one way to approach it, okay? So it's going to depend on what you're given and what it's asking for to figure out like what path you're going to take to get there. So different approaches here. So if your given and unknown quantities are both in moles, you can start with the amount of the given substance in moles and go directly to the amount of unknown substance in moles, okay? So you don't have to convert this to mass first. You don't have to do anything else like that. So if it gives you moles and it wants moles, it's a one-step conversion. If it gives you moles and it needs to know something in grams, you're going to have to start with what's given in moles and then convert that into the unknown amount of moles. So if you are given carbon dioxide and it needs water, you're going to have to convert it from carbon dioxide into water first, okay, as far as the mole conversion. And then you can convert it into mass, okay? So we're always starting, this would be like probably your reactant side or just whatever's given here, converting it into the other substance, the moles. This would be your mole ratio, would be what you'd use here, and then into mass. Another example here is if you are given mass and the unknown is in moles. Okay, so you would start with the amount of mass that's given, convert that into moles so that we can use our mole ratio here. So start with mass, convert it into moles, and then you can use your mole ratio in this step to figure out the unknown amount of the moles. The last type of question you guys might see is that the given in the problem is mass in grams and the unknown is also in grams. These are the longest ones, and these are the ones I'm going to have you guys practice today because these are the ones that are most often used. And I know it's not easy, but I know you guys can figure this out. I know you guys can do this. So on your questions today, on your assignment, there's 4 questions, and you're using this workflow to solve them. So you'll be given the mass of the starting substance. You need to figure out the conversion. So you need to have the starting mass. You're going to convert that into moles. Okay, so let's say I'm starting with water here. So if you start with water, I now need to figure out how many moles of water there are in that many grams. Now let's say I'm converting water and I need to know how much carbon dioxide will be produced. So I am going to use my mole ratio at this point. Okay, so what is my mole ratio between the water and the carbon dioxide? So that's going to be converting the water into carbon dioxide. Now at this point, you can have your carbon dioxide. You are going to then convert it into the mass. So you're going to have the molecular mass of that substance. So if it's carbon dioxide, you would add it all together and then you could solve. Okay, so I know they're long, but we'll do one more example. So here's an example of a kind of the same type of problem that you'll have in your assignment. So if you start with 5 grams of dihydrogen monoxide, how many grams of oxygen will be produced? And this is the last slide, okay? So just kind of giving you a heads up. So first you want to write out your equation and balance it. Okay, so if we have dihydrogen monoxide, it's producing oxygen, and in this case, we know that there's going to be hydrogen left over. Most of these questions will be a little more direct. I'll give you every little piece. So we start out with water. It's yielding hydrogen and oxygen, and then we're just going to balance this out. We have several different mole ratios. Okay, so if we're starting with 5 grams of dihydrogen monoxide, how many grams of oxygen will be produced? This one in the center is the one that we're going to use. Okay. And then you need to convert to solve. So just like on the last slide, there's 4 steps, okay? And it goes exactly in the same order. So you start with 5 grams of water in this question, because it tells you that right here. So 5 grams of water, and we're trying to find grams of oxygen. So first we have to go from grams to moles, use our mole ratio, and then back to mass. So we're going to start with 5 grams of 5 grams of water. Grams of water is the unit that comes down and over. We're writing the unit first. Okay, so now we need to go from mass to moles for water. We know that 1 mole of water will be equal to 18.01 grams because I found the mass on the periodic table and I added it together. Okay, so now grams of water has canceled. We're in moles of water, which is great. Now you're going to write moles of water on the bottom, and we can go back and use our mole ratio at this point. So we're at a point now where we can switch from using water as our unit into using oxygen, which is what we want to do because that's what our question is asking. Okay, so if we're starting with dihydrogen monoxide, how much oxygen is produced? So here we have water on the bottom, which is our dihydrogen monoxide. We're going to use this mole ratio. Okay, so for every 2 moles of water, so 2 moles of water goes down here, you're going to have 1 mole of oxygen. So we're going to have 1 mole on top. Okay, so normally when we're writing moles, we've been always just doing ones, but it is not going to be 1 every time. It usually will not be 1 every time. So here we use that mole ratio. So we have 2 moles of water for every 1 mole of oxygen. Now our moles of water have canceled out. We're in moles of oxygen, which is great, but it's asking us for grams. So we're going to go ahead and convert that into grams. So moles of oxygen will go on bottom, mass will go on top. So we know that 1 mole of oxygen will be equal to its mass. Note here, this is important, that the mass of oxygen gas is 31.98 grams because this is O2. It's not just oxygen. And we know that because oxygen is one of the diatomic molecules. So when we wrote this out originally, it was an O2, which has to be accounted for down here. So just make sure that you're using 2 oxygens for the mass. So now we're done because these moles of oxygen have canceled. We're left with grams of oxygen, which is where we wanted to be. And so now you can solve this algebraically. So we should end up with 4.44 grams of oxygen. So if we started with 5 grams of water, and this specific reaction happened, we would end up with 4.44 grams of oxygen. Okay, so that is it for today. You have 4 practice questions, and they will all be done in this format on this slide. So if you want to pull up this slide to kind of help guide you, or the slide previous to this that had kind of all the workflows on it, that will be useful. Please let me know sooner than later if you're not understanding. It's very important. So let me know, and if we need to schedule any kind of like Zoom meeting or whatever, we can do that. So I hope you guys have a great rest of your day.